My name is Mark Kimsey, research staff with Intermountain Forestry Cooperative at the University of Idaho. So kind of a little bit on the other side of the mountain and on Montana's turf over here, but we collaborate with Peter Kolb quite a bit. So we enjoy this opportunity, appreciate the time to come over and talk. And what I want to talk about today is something that we all have worked on, we've all acknowledged, but maybe I can just kind of give you guys a little bit more insights of, what our trees are experiencing on this landscape out here, which is very diverse. And so we're going to talk about soils of the Intermountain Northwest, and particularly their role in the forest health of the region, and productivity, and how we can use management to kind of improve that. And also how management can also have negative impacts on our forest soils in this region. So a lot of the work I'm going to present today has been about 30 years in the making, through Terry Shaw, Peter Micah, Marianne Johnston, and Jim Moore. Oh, come on in. Oh. So a lot of the work I'm going to talk about today in regard to soils and forest health in this region were done by these 5 individuals, or 4, can't count this morning. I did some of it, but a lot of the work was done in the 80s and 90s by these individuals. So let's just dive in. So presentation overview, I'll set the table, give you a little background of why we do what we do and what it means from a forest management perspective. To understand this, there's certain things we really need to know. We need to know the nutritional ecology of the different conifer species. We have to understand the different physical and the chemical characteristics of the soils and rocks of this region. And we have to then put that all together and how that affects conifer health and productivity. So how does climate, how does soils, how does fertilization or forest management for that matter, any kind of forest management, affect long-term health and productivity? And that's where we'll get into maybe a little bit of best management practices at the end. So let's set the table. So we know this, right? We've been foresters. We work out in the woods. We know what drives forest productivity. Everything needs light, right? Everything, you have to have light. You have to have water. For different kinds of species, you have different temperature regimes that they inhabit. Regardless, though, everything needs nutrients. We need nutrients, right? Trees are the same way. They have nutrient needs. They have macro-micronutrients that are very critical for maintaining their health and their growth. From us, we're coming into this picture, we're wanting to manage the landscape. So what we do can affect the site's nutrient capability, but we have to work within the temperature and the moisture regimes that a site is unique to. In other words, we can't really affect, other than with light, we can, through density, we can affect light, but latitude, we can't affect latitude, which is sun length, amount of light that a stand or an area is going to get. We can't affect elevation, right, which is critical of moisture and temperature. So all of that plays in. We have to work within that context. So with nutrition, though, that's one thing we can have an effect on, which means that as you manage your forests, you actually need to manage for nutrition as well, because nutrition affects forest productivity. And you have to look at this also from a time perspective, because from a time perspective, while what we do today will have an impact, what we do and our future generations do has a cumulative impact on the landscape. And so we can leave our stands better for the following generations, or we could actually make them slightly less so. And so managing for nutrition is key for maintaining long-term forest sustainability. And in some cases, a lot of times, forest certification requires you maintain that site sustainability. And nutrition is going to be a critical part of that. So looking at this historically, going back into the 1960s and 70s, there were three individuals that really did a lot of pioneering work about the nutritional status of this region: Scanlon, Lowenstein, and Pitkin. A lot of work was being done on the west side. And we say west side, we're talking about, the Willamette Valley, over on the wet interior, the coastal ranges, the west side of the Cascades. A lot of work was being done over there with nitrogen fertilization, because at that time a lot of large private timber companies, Weyerhaeuser, Georgia Pacific, a lot of those companies owned a lot of land over there, and they had the water, but they also realized they had nutrient deficiencies, primarily nitrogen. So they were doing a lot of nitrogen studies out there, and they were coming up with formulations. Scanlon, Lowenstein, and Pitkin came through and said, well, let's take a lot of that work the west siders are doing, bring it over here to the east side, see what happens. Well, they did. So they looked at different kinds of responses by different species due to different treatments. And all I want to show on this and get from this particular graphic is they did a fertilization, a thinning, a thin and fert. They looked at basal area and height growth and volume growth by different species, so Douglas fir and Grand fir. And basically all I want to show is the range of variability in responses to those treatments. These are just distribution curves of responses. So typically they're positive. Typically if you combine the fertilization and thinning, it was additive. So you had a thinning response or you had a fertilizer response. If you add the two together, that's typically what you get with the fertilization thinning. But look at the range of responses. Oftentimes there was very high response, and you get a negative response. You'd actually reduce your growth rates on certain sites. Why? They were getting inconsistent results to these different treatments. So they wanted to ask the questions why. That paper, published in 1979, was the impetus for the development of what they called the Intermountain Force Tree Nutrition Cooperative in 1980. Just last year, the members changed it to the Intermountain Forestry Cooperative, as a lot of the work we do is now not only nutrition, but a lot of other aspects in forest management that we look at. But that paper was the impetus of trying to answer that question of why. Why do we get such different responses to different kinds of treatments on this landscape, particularly in the interior Northwest? So over the last 35, 36 years, of course, membership changes within any cooperative at any given time. This is our current membership list, but essentially members were public, so state or federal, and we also had private, small to large private landowners. And over that last 36 years, all these little yellow dots represent all the research sites we've installed over these years. Yeah, it's a lot of work. You can see why I said we had to really give a lot of credit to those individuals, because that was, and to the membership of this cooperative, because they had some really long-term vision of where they wanted this to go. And today we're going to do a little summary of what we found, kind of summarizes the results of all these different studies. So to begin with, we had to settle on a classification system here in the West. Whenever you have to do any kind of experiment or research, if you just go out and put plots out everywhere and look at response to your treatments, you're just going to get a scatter of response to your treatments, because it's going to be so variable, right? Everything is variable on the landscape. So if you don't bend things up into different types and sample across that, you're just going to get a scatter approach. So what we had to do is we had to define classes of sites. A lot of the early work showed that soil and climate was critical, but their experimental designs were confounded because they did not break things down by moisture regime or soil type. And so what happens is they couldn't tease that effect out of their experiments. So it was all confounded. 1980, did we have tablets and smartphones and GIS and all that kind of stuff back then? No, we didn't have that kind of stuff. I mean, GIS was kind of starting a little bit, but so we relied on the good old tried and true way of just letting a site define what that site is, right? Which is, for climate, we use Pfister, we use Cooper, we use the Daubenmeier system. It's just let plants that are growing on a site tell you what that site is. And so for you guys here in Montana, you know, there's the Pfister. That he developed the forest habitat types in Montana. For us, we have Cooper over in northern Idaho. But the Forest Service did a lot of work developing habitat types for the different regions. How many are familiar with what we call habitat typing in this region? Okay, some of you have. Just to give you a little background on what habitat type is, essentially what it does is it's a continuum from the warm dry to the cold wet. And it tells you what particular species are indicative of those kind of moisture temperature regimes. So when you see ponderosa pine, you think what? Warm dry, right? When you think subalpine fir, what do you think? Cool wet. When you think grand fir, kind of warm wet, right? So it makes sense. We can bin up our climate just based on, you know, our indicator overstory species is what we call them. So if we're in our pine, dub, fir types, we're in our dry sites. If we're in our grand fir, we're in our moist sites. And when we're in our cedar hemlock sites, we're on our wet sites. So you think of some of the cedar groves over by Libby Troy country, you know, that's wet, right? You think of some of the areas around here with all our pine sites, dry, right? So, okay, great. Now we can start binning up our sites on climate. The key is how do we do this from a soils perspective, right? How do we get at what is a productive soil versus what's a non-productive soil? And this we thought of, and not me, they. That's what they thought of. It's like, how do we start binning this up? You know, the NRCS has done a really good job of creating a nice, almost continuous. If you've got into Web Soil Survey at any point in time, there's a lot of nice soil maps that cover the regions. But back then there was less so. You never had Web Soil Survey back then. A lot of the soil survey maps were not continuous enough. They didn't cover the landscape that we wanted to look at. And so what did we have to fall back on? We fell back on geology. I mean, soils have to come from something, right? You know, soils come from weathered bedrock material. So for the most part, a soil profile should reflect the parent material or the geology it came from. We do have geology maps. We can use those. And so for the region, we went to state geology organizations, and within Oregon and Washington, Idaho, and Montana. And we said, okay, let's start binning up our rock types, but how do we do that? You know, foresters are not geologists, right? That's just, we're in there, we're looking with forestry, but from geology, we had to bring geologists on board. We also had to bring some soil scientists on board, because what geologists do is if there's a soil less than 10 feet over a particular rock type, they call it overburden. They don't map. It's not even there. They don't. That makes sense, right? They're geologists. They're mapping rocks. They're not mapping soils. But where's a tree root? Where's the trees? Where's the tree roots, right? They're in the overburden. So if you have overburden that's not derived from that rock, you have something completely different going on there, and you have to be aware of it. These are the biggest that we have to work with. Superficial deposits, often they map glacial till deposits. That's good. You know, a lot of our glacial till, they have mapped. Where they don't have it mapped, though, is when you get into higher elevation sites. As those glaciers came down out of Canada, they're grinding their way down over here. Aspect makes a huge difference. You'd have deposits where they came up and over a hill, came over the top, and you get all this overburden that they won't map of glacial till up on our higher elevation sites. When you get down to lower elevation flat lands, then it's mapped because it's deep, right? Up there it's not deep. So they'll say it's a certain rock type up there, but then you drive up there and you get all that nice, round, cobbly material sitting up there. Well, that's glacial till, which who knows where that came from. Typically it's local source, but you could be having some stuff come down out of Canada too. So we had to be aware of this environment. So we now had a way of binning up our sites. But before we start binning up our sites, we have to understand something about the species that inhabit those sites. What are their we call it the nutrient ecology. What does a particular species need to be healthy and productive. Every tree is something different, right? So let's talk about that. Every plant needs what we call macro and micronutrients. And this table is a description of some of the major nutrients that a plant or a tree needs. There's more than this, but this is the primary ones that we see the most deficiencies across this region. So we have nitrogen, we have phosphorus, potassium, sulfur, copper, and boron, and they all have different functions within a plant species to some varying degrees or another, depending on your plant species. And here's their source. So let's look at nitrogen. Nitrogen is very important in photosynthesis in your biomass production. Look where it comes from, the atmosphere. Is minimal. I mean, basically nil comes from the soils. So where are we getting our nitrogen? It has to come from nitrogen-fixing species, taking it out of the atmosphere, fixing it, putting it in the soils, and then over time, as plants take that up, and that organic matter gets returned to the soil, it gets released through decomposition, the plants take it right back up again. But because this atmospheric deposition, we don't have a lot of deposition in this region. So nitrogen tends to be fairly deficient. We're going to see that here in a minute. Phosphorus, not so much. We have a lot of phosphorus in our rocks. Apatite, one of the primary minerals in our rock types. A lot of apatite in our soils. Apatite, one of the primary building blocks of apatite is phosphorus. Not going to have a big deal with that, but it's important. It's an important nutrient in our soils. Potassium, important for defensive chemicals and for stomatal control. Now, how many were in with Peter Kolb's talk this morning with drought? All right. Did he talk anything about stomatal conductance with drought? Briefly. Okay. Stomates, what do? They allow carbon dioxide to come in, oxygen, and moisture to go out, right? So what happens if you have a potassium deficiency, you're not regulating your stomatal control, and you get a drought? What's going to happen? They're going to dehydrate. They're basically going to. That's why if you get on a site that say has had a warm, moist climate for a while, and it's typically a Doug fir type stand, you get a lot of grand fir coming in underneath of it. What happens when a drought hits? They die, right? Because they're on the margin. And why is that? Because grand fir, they pump and pump and pump, and usually they inhabit the moisture sites. So moisture typically for grand fir is not a problem. But if water becomes a problem for grand fir, it will fall out. And the reason why is it's stomatal control. So if you get on a site that has low potassium, so not only are they having problems regulating, closing and opening their stomates, and then you get a drought on top of it, it's a double whammy. Sulfur, important in photosynthesis. What's really critical here is there's a feedback loop between nitrogen and sulfur. If you have a nitrogen deficiency and you have a sulfur deficiency, you could put nitrogen back on there to alleviate a nitrogen deficiency. But if it doesn't have the sulfur it needs to properly maintain that photosynthetic pathway, you're not going to be able to overcome it by just putting nitrogen out there. So we have to keep this whole nitrogen-sulfur cycling in mind when we are looking at deficiencies across the landscape. Also, look at its source. It's rock and atmosphere both. Now, if you were down in the Yellowstone country, you'd have a lot of sulfur, because what kind of rocks down there? Gypsum, right? A lot of gypsum, which has a lot of sulfur in it. Not a lot in the areas that we work in, but you still have some minor degrees of sulfur, but not to the degree. So some of it is through atmosphere, but it's not much. Because why? We don't have industry. Where's the primary source of sulfur if it's going to be artificial to this region? It's going to come from volcanic activity or it's going to come from industry. We don't have either of those, which is good. Because there's a lot of volcanic activity we can worry about, a lot of other things. So we have to be aware of this. We have to be aware of the nutrient ecology and where it comes from and what we do. And so we can then look at requirements. What do our species require? Our firs are some of the more higher demanding nutrients. In fact, grand fir, Al Stage over at the Rocky Mountain Research Station in Moscow used to call grand fir the nutrient hog. And the reason why he calls it the nutrient hog is relative to all the other species, it consumes a lot of site nutrient capital. When you get into your pines, you think of western white pine. It's more of an open, it's more of a shade, well, it's more of a, it's a species that inhabits kind of the moisture range of the pine range. And so it typically has a higher requirement of nutrients than some of our ponderosa pine and lodgepole. Western larch is kind of, we still put that into the oddball category. We still don't quite have everything wrapped up on what happens with larch. Primarily because it's a what? It's a deciduous conifer. It's kind of a throwback. It's hard to really kind of nail down larch. In fact, we've done a lot of nutritional studies here in Montana, and we compare them to research we've done in Northeast Oregon and Idaho. They're different. And so, whereas some species are more constant, larch is less so. And we still have a ways to go on trying to truly understand the nutritional ecology of larch.
What do you think will spruce be in that?
My guess would be in the moderate to low. I would think it'd fall somewhere probably right about in here. But we haven't looked at actually Engelmann spruce. So I'm going on a limb to estimate that. So just to show you how much nutrients can be stored above ground in these different species, and we're looking at Douglas fir and grand fir. This is looking at bollwood, bark, limbs, foliage. And so this is kind of a summary of how much pounds per acre can be in a particular tree species. So Douglas fir, nitrogen content somewhere around 400 pounds an acre above ground of nitrogen. This is why we started calling grand fir a nutrient hog. Over 700 pounds an acre of calcium above ground. What's calcium for? Cell wall structure. When you think of a grand fir, it likes to grow. It has a lot of calcium in its structure, a lot of calcium in the foliage. Think of the crown, the architecture of grand fir versus a pine or a Doug fir or a larch. A lot of crown, right? A lot of foliage can hold those needles for a long period of time, so it's going to have a lot more calcium buildup. If we looked at aluminum, it'd be even more stratospheric on the concentration. We're not as concerned, of course, about aluminum, but a lot of nutrition above ground has helped. So this could be an issue. It's not an issue, but it's critical when you think about forest management, right? If we're doing whole tree harvesting, tops, limbs, everything comes off, we pile and burn the slash. Essentially, these trees are miners, right? They're taking nutrients from the ground, taking them up, holding them. Yeah, they have litter and dieback, goes back in the soil, but if you take that off, you're taking nutrients. Now, is that good? Is that bad? It depends on your site. We're going to get to that as we go along. So what we had to do is we had to come up with different ways of assessing nutrients. And that way, that allows us to be able to say, okay, on this particular site, we have problems. Or on this particular site, we don't have problems. This is a good site. We don't have to worry about nutritional deficiencies. A couple different ways we went about doing this. One way was to develop average levels of variability of nutrient concentrations across the region of Montana all the way to Oregon. And what essentially this allows us to do is it says what's the distribution of nutrients in these different species across this region. So then when we go and get another spot and we look at its concentration, we can compare it regionally to where it falls. And we'll have a graph, and I'll show you that in a second. We can then use that to say, okay, where is it in reference to what we call critical levels. A critical level is where if you fall below critical level, what would that mean? That means that no longer is that nutrient in optimal status for forest health and productivity. So that means then, if it's below a critical value, it's probably going to respond to some sort of a nutrient input. So we can look at these in different ways. And so this is what we call, this was that cumulative distribution I was talking about, along with critical levels. And let's walk through this. So we're looking at nitrogen now, one of the most critical nutrients in our forests, for 4 different species. So we're looking at grand fir, Doug fir, lodgepole, and pine. So as they said, here is ponderosa pine out here. and this ranges from 0.7% to 1.7% nitrogen, and this is in the foliage. We use foliage tissue as diagnostic. So what we'll do is we'll go grab a foliage sample, dry it, weigh it, grind it up, send it in for nutrient analysis, and we'll get a percent concentration of that nutrient in that foliage. We can then say, okay, where across our region does it fall relatively? So relatively, our soils range, or our foliage nitrogen ranges from 0 to 100%, and there's our concentrations in that foliage. So most of our sites for all our species would fall somewhere in this range. So if we came up with, say, 1.3% nitrogen in a foliage sample for Douglas fir, we just come up here to 1.3%, it'd fall up here, which means that if we came over here, about 95% of our sites are below that value. What does that mean? If 95% of our sites are below that value, that means they're less than that 1.3 value. Now what's really interesting to look here is look at this value, our critical level for Douglas fir, 1.4%. So let's draw the line up here from that 1.4, and we hit our yellow dashed line for Douglas fir. This means that over 95% of our stands are deficient in nitrogen. That's eye-opening, because why is nitrogen important? It's important for photosynthesis and growth. So this means that, and then let's look at ponderosa pine. Its critical level is 1.1. You come up here, here's the ponderosa pine curve. So this means that approximately 85% of our stands are fine from a nitrogen perspective. So why do you think there's such a dramatic difference between Douglas fir and ponderosa pine when it comes to nitrogen? Why do you think that is?
The way they absorb it?
It's how they use it.
Okay.
Ponderosa pine, think of the environment that ponderosa pine inhabits. Pretty much your low elevation, dry sites, right? They're really conservative with their nutrients, really conservative. They'll just sit there on a site. They're not into producing a lot of biomass. They just sit there. You could actually fertilize ponderosa pine with nitrogen and you won't see a response. Now, if you give it enough moisture, it might, but relative to, say, your grand fir, it won't. And the reason why is pine is very conservative. Douglas fir, on the other hand, or grand fir for that matter, it wants to grow. It wants to produce biomass. So if you're deficient and you put nitrogen on there, you're going to see a response. Looking at, say, potassium, on the other hand, 4 species again, pine, grand fir, Doug fir, lodgepole. Critical levels, somewhere between 0.5% and 0.6% is the critical levels. Regardless of species, 80% of our stands, regardless of your species, is not deficient in potassium. There's a reason for that. Where does potassium come from? Nitrogen, it had to come from the atmosphere, right? Potassium is rock. Most of our rocks in this region have a significant amount of potassium in them. And so as that rock weathers from the primary minerals and releases the nutrients, there's a lot of potassium available, so you're not going to have that kind of deficiency. Where you run into these deficiencies when you get into some of the rock types in this region, which we're going to talk about in a minute, primarily your metasediments. I'm just going to skip over that real quick. So, summary of your common nutrient deficiencies in the regional conifers is you can almost say always nitrogen will be limiting, except for when you get into certain species. Potassium sometimes limiting, depends on your rock type. Sulfur and boron very commonly limiting. Boron does come from rocks, but it's minimal. There's minimal amount in rocks. So what happens with boron is we often will see a boron deficiencies in our forests. The reason for that being is not only is there minimal inputs, but the cycling of boron in the forest is what we call tight. In other words, the minute or some piece of organic matter is broken down, decomposed, mineralized and that boron is released into the soil, plants take it up just like that because it is a critical nutrient, but it's in such low supply that it's a very tight cycle. And so what we often see is nitrogen, sulfur, and boron you could put as our three main nutrients that we have deficiencies on for most of our species. Yes?
I'm wondering how soil pH affects nutrient availability.
That can have if you think of your limestones and your dolomite soil types we have in this region with high pHs, most of your availability is more in your acidic soils. Mm-hmm. So when you have pHs, what we have like 5.5 to 6, typically better. When you get higher pHs, when you get into the 7s. Now I'm not sure what your soil types around here are for your dolomites or your limestones, but my guess is they're going to be up in the 7s. I don't know if you see that. I haven't done much work in this area for that.
West of the divide, they are up in the 7s.
Yeah. So, but there's something else that's critical, as well as pH, is when you get into those soils that have those pHs, what are the minerals that are making up those soils? Oftentimes, it's going to be your dolomites and your limestones. We're going to talk about that from a nutritional perspective coming up. So that's a good question.
I have one question.
Yeah.
Is there any, is transport through the soil a factor in any of these equations?
Because the cycling is so tight for these particular nutrients in our forest soils, unless you put a high dose rate, say you're fertilizing with nitrogen, let's say. If you're fertilizing with nitrogen to the degree that you're on a coarser textured soil with a lot of water inputs, and it's to the degree that you overcome any kind of deficiency limitations, you might get some leaching out of that forest system. But at the rates that we're talking about and the amounts that are commonly available just inherent in the soil, no, not to that degree at all. In fact, a lot of the nutrients that we'll apply from a fertilizer perspective, they stay on site and they're taken up. In fact, when we do, and I'll talk about this a little bit later, when you do a nitrogen fertilization, say you put 200 or 400 pounds to the acre, you actually can see up to 8 to 10 years later a response to that fertilization that far out. So it stays there. It stays locked up and it cycles. Those plants take it up and return it. So leaching is less of an issue for us. Except for there are circumstances, but those are very rare. So now that we have kind of a basis as we set the table there for what kind of nutrients our trees need and what some of our limitations are, what we had to come and start to understand was, what do we have from rock types? What are we dealing with out here? What's the physical and chemical characteristics of the soils and rocks that our stands are residing on? And so this is where we start working with geologists, defining the primary sources of our soils. In this region, the primary source is going to be either going to be some sort of igneous rock or a metamorphosed rock, particularly here in western Montana. South of here, you'll get some of our volcanic rocks, or basalts. They're the lava flows. It's the magma, the liquefied magma that came to the Earth's crust, crystallized as it moved across the soils. And those are what we call volcanic soils. We also have plutonic soils. These are what we call granitics. These cool slowly inside the Earth's crust, and over time, through uplifting or through erosion, they're exposed. Because they cool slowly, it allows larger and larger minerals to form. So when you're on granitic soil types, what's the characteristic? How many of you are you aware of granitic soils? You've driven on granitic soils. What's kind of characteristic of granitic soil, texture-wise? It's kind of coarse, isn't it? Sandy, right? Yeah, very sandy. Not a lot of water holding capacity, not a lot of soil development, right? Soil development is what we call really fine textured, deep soil. We would kind of it has a clay content of 15 or 20%, silt content of somewhere around 50 or 60%. No, its sand content could be 60, 70%. So the reason for that being is as it cools slowly, it forms large crystals. Because it has large crystals, mineral structure, it's going to form a coarser textured soil. Whereas when you have a volcanic soil, which cools very rapidly, what happens? those minerals don't have time to form large crystals. So they crystallize immediately. And so they form these really small minerals. Which what happens? It has higher surface area and it forms finer texture soils, which is your clay soils. We're going to talk a little bit more about why that's important from a nutrient retention perspective a little later. Then we have our sedimentary rocks. You know, essentially your sedimentary rocks are just they're just rocks that were derived from other rocks. Weather, you know, water, wind, erosion, you name it. If some other rock was weathered to the point where it was transported off-site and it got buried just through some sort of a kind of a consolidation process. It turns into shale or sandstone or siltstone or claystone. Essentially, in all siltstone, claystone, and sandstone means is that's sand, silt, and clay, right? So just depending on the particle size, it just developed wherever it was settled in some sort of a lake bottom or valley. It just depends on the rapidity of the water deposition at the time that it was laid down. So we get different kinds of sedimentary soils. We have unconsolidated soils, or glacial tills, river deposits. You know, we're all familiar with our glacial tills. We'll see a lot of deposits of those in this region. Metamorphic rocks. I call them pressure cooked rocks because essentially it's either a plutonic rock, like our granitics, that due to tectonic activity, you know, there's a lot of grinding and smushing and movement in there's crust and it deformed it through heat and pressure. And so what happens is that's critical actually because if it's been pressure cooked, there's a primary building block of all rocks and it's silica, glass, right? What happens, say you had a piece of glass and it melts. Imagine that melting within the framework of the rock formation. It makes it harder. It actually makes it harder to weather. And so when you metamorphose a rock and you melt that silica structure, you deform all those bonds and you make those bonds different in that rock structure in such a way that it actually makes it harder to weather. That's critical when it comes to developing a soil profile. It's critical when it looks at the weathering ability of your minerals. And then we also have to be aware of our superficial deposits, as we mentioned below. So, Jim Moore, our esteemed director, started in 1980, came up with this term, good rocks, bad rocks. And of course the geologists, when they first heard this, it's just like, they got kind of glum. And they go, good rocks, bad rocks. Well, is there good trees, bad trees? It's like, of course not. It's all good trees. But in rocks, in our environment, we have to look at these rocks from the perspective of, do they have a balance of plant essential nutrients in their geochemical makeup? And this is critical because rocks must be able to develop a soil profile, and they have to develop a soil capable of supplying and holding nutrients on the site. If a rock has a lot of silica in it, it's not going to be able to give you a lot of supplying or holding of nutrients. And we're going to show that in a minute. So we have to be aware of this chemical content and the weathering components to define this whole good rock, bad rock continuum. And this is all defined on site. You could have a good rock on a site with low moisture, and that particular site would actually be less productive than a site on a bad rock, say at higher elevations with a lot of moisture, right? Or a volcanic ash cap. If you had some volcanic ash over a bad rock at 4,000 feet on a north aspect, you could have a nice grand fir cedar type as opposed to a pine type at low elevations on a good rock that just kind of sits there. So it's all about tying site and rock source together. It's really also critical is that there are secondary sources of nutrients, and of course that just comes from the soil organic matter decomposition and nutrient cycling. And so that's the other thing you got to keep in mind too when we're doing this, is because when we're in more moist soils, you're going to have a fast, rapid cycling of those nutrients. Those microbes are happy. You know, it's always 70 degrees, and it's always 40% moisture content. Whatever it is, it's just they're happy. When you get into cold, they're just like us. Microbes are just like us. They're going to slow down when it's cold, and they're going to stop when they're dry, right? They're just not going to be as active, which allows what? Buildup of organic matter, and it's not going to decompose as much. So when we come into the weatherability range, we have to be not only aware of our climate, but what kind of minerals that are in these different kind of rock types and how they increase in weatherability. So, when I talked about basalt and granite, remember basalts rapidly cool and form fine crystals, and granites cool slowly and form the larger crystals. You can see that difference. These are just microscopic views of so they call a twin graph of kind of a slice of a rock surface. And you can see how fine that is. So that's going to weather to form a clay soil with a lot of surface area, a lot of nutrient supply and holding, cation exchange capacity. A lot of clays have a high CEC. Granitics, because they have a lower surface area, they're going to have a lower CEC, and they're going to have lower water holding capacity, all critical things. But if we look at our common minerals, here's our rock types, or we have some metasedimentary rock types up here, kind of our igneous metamorphic rocks here, we have some sedimentaries here, and these are the minerals that kind of inhabit these different rock types. Here's quartz, very top of unweatherability. What's quartz? SiO2, right? Silicates, glass. If somebody says go plant your trees in a bunch of quartz, they're not going to be happy, right? No. Not only is that soil not going to weather or form any kind of nutrition, that soil, there's not going to be a profile development on a quartz-driven soil. There's not going to be nutrient holding capability. So forest health, can you imagine on a site dominated by minerals and quartz, your forest health is going to be pretty poor, right? As we get into our feldspars and our micas, these are kind of more of our granitics and our basalts as we come down here. Pyroxene and olivine are in our basalts. Has some feldspars. A lot of our potassium feldspars and micas are granitic rock types. They weather. They weather to a degree that it forms a nice surface soil. Carbonates. Think just east of town here, we have a lot of limestone. I think we got some dolomite too. They're going to be carbonates, either magnesium carbonate or calcium carbonates. So calcium carbonates would be your limestone. Your magnesium carbonates would be your dolostone. Carbonates is what? CO3, right? Carbonate. What do they put in your fizz drinks? Like Coca-Cola and stuff. A lot of carbonation, right? Carbonates, when it gets into a lower pH setting, dissolve rapidly. So, and you have carbonate-bearing soils, those mineral bonds break down, allow you to form a deeper soil. What do you need, though? You need water. Everything needs water. Mineralization needs water. Weathering needs water. You could take carbonate-bearing rocks at a low elevation with no annual precip or effectively none, and you won't have a soil development if you took that same rock type and moved it up several thousand feet into a higher precip zone. So, relative to the climate that those rocks inhabit, this is kind of a weathering perspective. And so what we can do then is, from a rock geochemistry perspective, we can say, okay, we have these minerals. What makes up? What are the nutrients in this? So here's our major elements in our different rock minerals. Oxygen, silica, aluminum, titanium, iron, manganese, calcium, magnesium, potassium, sodium, phosphorus. We also have some trace elements, nickel, copper, and zinc. And essentially, what you see in blue are what we call plant essential macronutrients. Trees need these nutrients to grow and be healthy and productive. The orange, same thing. They're plant essential nutrients, but they're micronutrients. So they have a lower concentration in these different rock types. Still critical. Our black, they are important, but they're not critical. Red, unsmiley face. There's a reason I put an unsmiley face in. Silica. If that rock type has a lot of silica in it, number one, the plants really don't care about that. They don't need it to any significant degree. And if it has more silica in a particular rock type, it has less of everything else, right? So let's look at this from three different kind of rock continuums. Let's look at it from a basalt, a granite, and a metasedimentary. So looking at SiO2, that's quartz. So looking at quartz in our rocks, every rock's going to have quartz. Every rock's going to have SiO2 in it because it's the basic building block of all rocks. But in basalts, typically we're at about 50, a little over 50% of basalt rock is SiO2. Go into a granitic, that jumps to a little over 65%. And look at these metasedimentary soils. Over 80% on a whole rock geochemistry. So if you had a pound of rock, 80% of that rock is silica. So if you have that much silica, that means you have less than 20% of that rock is actually of something that's meaningful to a tree. And you can see that looking at your oxides. These are different kinds of oxides: iron oxide, calcium oxides, magnesium oxides, potassium oxides, sodium oxides. And you can see that our basalts have a lot of iron, a lot of calcium, a lot of magnesium, a little less potassium and sodium than, say, our granitics. And that makes sense because sodium feldspars and potassium feldspars are some of the primary minerals that make up granites. So it's not a surprise that they're going to be a little higher. But look at them all relative to our metasedimentary soils. If you're going to have a lot of silica, you're going to have less of your other oxides. And these are your critical plant essential nutrients. So what this means is if we have a forest growing on our metasedimentary rock types, what does this mean from a nutritional perspective? They're going to be challenged, right? You're going to have some serious challenges when you look at our metasedimentary rocks. So bring this back into context. Remember, we had to come up with a classification system. We had to say, what is our climatic regime? What is our nutrient regime? Every rock is going to have a different signature from a nutritional perspective. So we can't, there's absolutely no way we're going to be able to sample everything out there, right? There's just no way. So we have to come up with an index. What kind of bin can we put these rocks into? One way of binning them up is what they call the Weathering Potential Index, or WPI, which is developed by Reiki back in the 1940s. And essentially all it is the ratio of your cations, which is sodium, potassium, magnesium, calcium, times 100, divided by those same cations plus silica, aluminum, and your iron oxide. So these are your structural components. The primary structural components of a rock is silica oxides, aluminum oxides, and iron oxides. So you take that, and because you multiply this top by 100, the higher the WPI, the more weatherable it will be. So we can rank this based on those. And so what we can come up with, looking at those three rock types we presented in the previous graphic, we can see, okay, our basalts, because they're going to be high in what? Calcium, magnesium, potassium, sodium, they're going to have a higher relative weatherability index comparatively. So here's our basalt, range somewhere between 16 to 29. Granitics makes sense. They're going to be a little less because they're going to have more silica relative to your basalt. So, but we have a range in here of 7 to 35, and that's because there are different flavors of granite. When I say flavors, it means you can have quartz diorite, you can have granodiorite, you can have tonalite, you can have, there's probably half a dozen different kinds of granitics that are out there, and they all have different levels of silica. Some are high, some are low. Some have maybe 35% silica, some have 65% silica. And so that gives you a different range, right? Because silica, the more silica you have, the lower this is going to be. Less silica, the higher this will be. So we had to be still aware within each of these different kind of bins of our WPI, these factors. And that really was critical when we started looking at metasedimentary rocks, because we hypothesized that most metasedimentary rocks were all bad rocks. We thought, you know, when you looked at that previous graphic, which showed metasedimentary with high silica content, it's just like, oh boy, we have issues with metaseds. They're going to be bad. But look at the range, 1 to 75. So this means we've got some really bad metasedimentary rocks. And this would suggest, oh, shoot, maybe we actually have some good metasedimentary rocks. So what's going on here? So that made us have to dive even deeper into the geology question and talk with geologists. And what it comes down to is this. Within this region, North Idaho, northwest Montana, a little bit into northeast Washington, and up into Canada. This was a giant lake bed of sediments. Got buried, cooked, pressure cooked, uplifted, weathered. In fact, when you drive around this country, you'll see these layered beds of pink and greens and reds and stuff, and sometimes they're this way, and sometimes they're this way, and sometimes they're this way. Well, that's all part of this whole, what they call the belt supergroup. This belt supergroup was first identified, guess where? Belt, Montana. That's when the geologists first ran into this. And it's just like, what are these pressure cooked rocks that we're looking at? And they start identifying it. And so essentially what it is there were these beds of siltstone, sandstone, and claystone that had been buried and pressure cooked. So those claystones turned into argillite, the siltstones turned into siltite, and the sandstones turned into quartzite. So what does that name quartzite mean to you when I say quartzite? When you say quartzite, it's quartz. And so all that material has different weathering capabilities, right? Quartzites, can you imagine what a quartzite's going to do? Well, actually, once you take glass, silica, and you just metamorphose and cook it,
It doesn't do anything.
it doesn't do anything. And so what we started to find out is these flavors within the metasediments were all based on what happened to the silica content in those soils and what was the carbonation. Were those soils, did they have some carbonates in them? You guys have a lot of Rivali in this country. We have a lot of striped peak over in Idaho. Now, what are we looking at? Weather PI. This is WPI index up here, but we also have some SiO2. So these are just percents. So WPI SO2. Look at the range in silica content, low to high, quartz or weathering potential high to low. Now, that's where we got that range of 1 to 75, right? Why was that? Well, see, there's a striped peak sitting over here. And if you come over here, here's another striped peak with carbonation. So what we're seeing here is, wow, okay, well, if there's a high component of carbonates, then striped peak is a quartzite. It's just pure quartz, primarily pure quartz. There's something in there, but nothing meaningful. Same thing with the Rivali. But you put this carbonate in, what's going to happen from a soil development perspective? It's going to dissolve, right? So you're going to actually get a deeper soil profile development in your striped peak carbonates than you are down here without it. Now, this is still quartzite with a little bit of carbonates in it. So if you have a lot of weathering of a rock that doesn't have much, a lot of nothing is still nothing. So when you get into these striped peak carbonates, while it can form a soil parent material, it's still not going to be as productive because it's just still quartzite that's got some carbonation with it. So from a forest health perspective, you all have driven around in our Rivali group. How many have experienced forest stands and known they were on Rivali? Anybody here? Okay. If you were on the Rivali or you came over to Idaho and you were on the striped peak, here's what you'd see. Grand fir with scolitis, grand fir with root rot, Doug fir with Douglas fir beetle. You'd have root rots and insect and disease infestations. Big time on these two rock types. In fact, you drive in there, it's just death on those stands. They don't like it. Why? There's nothing in there. Those trees are stressed. What do root rots and bugs love? They love stress, right? Exactly. So they're just like human beings. If we're tired and stressed out and eating processed foods all the time, what's going to happen to us? We're going to get sick, right? So what we've got going on here is we have some rock types that our trees are going to be stressed out. They're not going to have the nutrition, and so we're going to have forest health issues. So that is critical. That was very critical in our whole finding out of how we want to start binning up our site. One thing that you can use is the lighter colored the rock type, the less nutritious it is. The darker colored the rock type, the more nutritious it is. And why is that? Think about minerals. Iron, magnesium. Iron and magnesium are dark colored minerals. So typically if a rock type has a dark color to it, it has a higher content of nutrients. What's silicon quartzite? White. It's light, right? So potassium, or if you have even like sodium feldspars to some degree. Carbonates, not really, I mean, it's got some calcium in it, but it really doesn't have anything else. So it's all going to be light colored. So kind of rule of thumb is if you've got a dark colored soil, it's going to be fairly more nutritious, because there's the other aspect. If it's got more nutrients on that site, you're going to have more productivity from a forest health or a forest growth perspective, which means what? You're going to have more organic matter inputs going into that soil. You have more organic matter inputs in that soil, it's going to also be darker because that takes kind of a blacker hue, right? So if your SOM's high, your productivity's high, and you have high nutrients, you're going to have a dark colored soil. When you get into some of these metasedimentary soils, it's going to be light, because why? They just don't have a lot of those critical nutrients in them. So I often compare our dark colored soils to whole foods, and your white colored soils to processed foods. Trees see it the same way. If you have a light colored soil and a tree growing on that, it's like they're eating chips and sugar all the time. They're just not going to be healthy. So we can kind of come up with these rock type rankings based on this. Now again, remember moisture. You could have a good soil at low elevation with no moisture, and the trees aren't going to be doing anything. Now they might be healthy, they're just not going to be as productive. So we could say our granitics are going to have our good status, both from a rock nutrient and a soil nutrient perspective. They're going to have a finer texture, which means what? They're going to have more water holding capacity. They have a higher surface area, which they're going to have more cation exchange sites. So best soils, but remember, do you have the water? Just because you have a good soil doesn't mean it's going to be a productive soil, because everything has to have water. We have to have water. Trees need water. Trees need to have water. That's not good. What did I do?
Nope, didn't work.
That's the projector. That's not good at all. Oh boy. Oh boy. Well, we had a half hour. So let me go run somebody down. That's not going to happen. Maybe we can switch it. Let's see here.
When we did our forestry somehow.
Oh, no.
Yeah, first time.
No. I'm Martin. Martin Cooler.
What's he doing?
TV.
I guess projectors get tired too, so.
Okay.
All right.
So this is off and you just hit on.
Oh, okay.
So give it like 5 minutes.
Just give it 5 minutes?
Yeah.
Okay. 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 So we might as well just talk for a few minutes. So we can kind of talk about that slide a little bit more. So essentially what we were able to do was we could take our basalts and our granites. Typically they have a higher nutrient content. So we could say, okay, on those sites, probably nutrient limitations are going to be less of a concern than we do when we get into our metasedimentary soil types, which is where we want to make sure when we start binning up our sites we want to ensure that we capture that range of variability within our metasets. We just don't want to put everything on Strike Peak and not something else on, say, a Wallace. One of the other in that graphic was a Wallace. So we see less of issues on Wallace. So we don't want to say all rock types within a particular metasedimentary group are bad rocks. So we had to find out those different ways of looking at it. Then, of course, we had our mixed rock types, glacial tills. When we get into glacial tills, the problem we have with glacial tills is it's variable. What you have, and it can vary just within a certain, like between here and Kalispell, you can have many different kinds of glacial deposits. Why is that? Because not only do you have the local effects of glaciation, you have the continental effects of glaciation. So as those ice sheets scrape down out of Canada, they carried that material with them, as well as the local material that was grinding across. So you get this hodgepodge of all these different kinds of rock types together. And so it makes it a challenge. And so with glacial tills, this is what we say is when it comes to glacial till, it's a site by site by site analysis because it can vary. When we get into our sedimentary rock types, we typically look at those as low productive sites, typically. And the reason why that is just think of what sedimentary soils are. They are soils that have derived sometimes through several weathering processes of original primary minerals. So those primary minerals have been weathered, they've been transported, they've been weathered again, they've been buried, they've been uplifted, they've weathered. So you can imagine what happens to the nutrition in something like that. It's going to be lower. So
would that be true of limestone?
So with limestone, there are several different, I'm going to see if that works okay. It looks like it's coming on. With limestone, not only has it weathered, and you have a pH issue from a forestry perspective when it gets into limestone. And so in limestone, there are some plant essential nutrients, like calcium, but there's very little else in that limestone. And one of the other issues that we run in, that some of the foresters that we talk to here in this region is, depending on your climatic regime, a lot of these limestones act like sponges to water, but then they don't release it to the trees. And so you can actually have some fairly droughty soil. So maybe it's, while from a nutrition perspective, there might be a little bit more in there than, say, some of our metasedimentary soils that have a lot of silica in them. Sometimes it's a water issue when it comes into your limestones, particularly at these lower elevations. I don't know if that helped.
Yeah, I had read something like that at one point up on Wilson Park Forest. With limestone substrate, it was, you needed almost like 8 or 10 inches more precipitation a year to equal.
And oftentimes, while it might not necessarily be a nutrition issue there, it's a water issue on those soils.
But a lot of it is because the limestone's holding.
It just holds it. It holds it. It's just like a sponge that holds it. So let's hope that doesn't do it again. All right. So just a little summary over this real quick before we jump into a superficial deposit talk. The source again of most of our macro-micronutrients are the soil. However, nitrogen, sulfur, which are some of our most limiting nutrients in this region, they come from the atmosphere. And because they come from the atmosphere, that's why they're the most limiting, because we do not get those deposits. Our soils tend to be relatively young here in the Northwest, and so the geology signature on those soils is going to be pretty strong. So the kind of mineralogy and nutrition that's in what you see, or the mineralogy that you see in your rocks, is what you're going to see in your soils. So that allows us to use our geology maps to predict what's going to happen in our soils across this region. Nutrient richness, essentially our basalts are going to be the greatest, followed at the very bottom by our metasediments. And while we can have metasediments that can weather deeply, they're still fairly nutrient poor. Basalts and granites also tend to be fairly consistent across the region. Now you can have different flavors, but typically the same kind of minerals are in each of those different kinds of rock types, as opposed to when you get into your metamorphos and your sedimentary rocks, they're highly variable. Why? Metasedimentary are sedimentary rocks. Sedimentary rocks, they've been transported, they've been weathered, they've moved off site, so your mineralogy could be very mixed. So that's going to have a considerable impact on the kind of nutrition and weatherability of those soils. Again, the more silica, the less of your good nutrients. And typically when you have high silica, you mean you're going to typically have a shallow soil development, which means what? You're going to have less water holding capacity, you're going to have less nutrients, you're going to have coarser soil fractions. All that's going to have a detrimental impact on your health and productivity. Okay, I want to get into probably one of the most critical soil features that is in the Northwest, particularly for us here in the interior Northwest. If it wasn't for volcanic ash, we wouldn't have the forest stands we have across our mountains, or forested mountains in this region, primarily in North Idaho and northwestern Montana. And how many, that original picture on our title slide, remember that view of, did you recognize that as Crater Lake? Yeah. If it wasn't for Crater Lake, we wouldn't have the forest we have today, literally. So a quick definition of what volcanic ash is, and then we're going to talk about Crater Lake. So it's a wind-blown deposition of fine-textured tephra. And when we say wind-blown, just think of volcanic activity. It shoots the ash into the air. It hits the jet stream takes it downwind. So typically in our region, we're going to have what we call the ash, the kind of volcanic ash, which is your less than 2 millimeter size, so your silt-sized particles here. If you're close to the source, you'd have your pumice, 2 to 6 millimeters. If you look at Web Soil Survey, or you get your soil survey maps out, and sometimes you'll see some terms called vitrandic or andic or andesol. Those are different ways of classifying the degree of ash influence on a site. So if it's vitrandic, it's kind of mixed, less than 7 inches in depth. Andics is when you start seeing these nice ash caps sitting over some residual parent material weathered from the geology of that region. And then andesols are really deep ash caps. Now, in western Montana, when you get towards Libby, Troy, so kind of get more and more in the northwest part, you'll start seeing some redder ash caps. When you get over into this country and maybe more easterly and northeasterly, a lot of these ash caps become more tan, kind of grayer tan color. And the reason for that is, why would you have a red soil? Iron. So there's a lot of iron oxides in volcanic ash soils. So what happens, why would something be more red? You have an ash cap, ash, both from Mount Mazama, but one's red and one's tan. So why do you think one would be redder than another?
Heavier particles drop out.
Yeah. You're thirsty. Water. Weathering. Right. Iron will dissolve in water, right? So the more water you've got, so you have the cedar groves and everything over in Rawson up there in northwest Montana. So if you got a lot of water, it's going to weather those iron minerals and it's going to release that coloration. Whereas you get drier, move interior, you're going to have less moisture. You're going to get the continental climate. You get the continental climate, you don't get the weathering, you're not going to get those iron oxides. But what's critical, and we'll get there. No, I was jumping ahead of myself. I was getting kind of excited. So source, where do we get it? Of course, it's from the Cascade Crest. All those mountains along the Cascade Range has at some point or another actually had considerable number of eruptions, Mount St. Helens being the most common over the last 4,000 years. But here's Crater Lake. It doesn't even show up. You'd think a lot of these others would have some impact, and they do to some degree, but they cannot even compare to what happened to with what we got from Crater Lake. So this is a kind of an artist's rendition of what was Mount Mazama, is what the Indians called it back in the day. They estimate, based on kind of the structure and the slope of the side ridges of the mountain, that it was approximately the size of Mount Rainier. And now it's about 8,000 feet. So it lost, they call it a cataclysmic circular ring fissure eruption. So that's why you see that nice big even circle around. Basically it just blew out all the way around all at one time. Largest known eruption in the Cascade Range. They estimate that it reached about 10 miles into the atmosphere, so you can imagine it hit the jet stream and it came our way. And so about 3,000 to 4,000 feet of his dome was just blowing off, filled up about 300 feet of pumice and ash. In fact, if you've all been down to Crater Lake, you'll see those big mud flows. You'll drive through them. There's these white, massive banks of just mud. So it just filled up the valley bottoms with up to 300 feet of this material. It produced about 30 cubic miles of airfall material, volcanic ash. So to put that in perspective, it would have covered the entire state of Montana with about a foot of this material. That's a lot of material. It's a lot of material. And what happened too is a lot of that fell out in the Palouse region in Washington. Well, about, they called the mid-Holocene drought, just shortly after the eruption of Mount Mazama, a couple thousand years later. Very droughty conditions. So what happens? Volcanic ash is really fine textured. How many of you driven on forest roads in the droughty summers and there's volcanic ash around? It's just like you threw a bag of flour and drove through it, right? It's just this massive cloud of just dry soil blowing up and billowing behind you. Imagine that sitting out where there's very little vegetation, or it has an ability to erode through wind. You can imagine volcanic ash when it's really dry through that drought conditions, it has the ability to blow away, so to speak. A lot of that material out in that Columbia River Basin was picked back up and blown over into our region. And so what happens is you get this deposition of volcanic ash that has really defined a lot of our forests in this region. And this is kind of a extent comparison about with Mount St. Helens. This is the eruption zone in 1980 where we saw significant amounts of volcanic ash. This line here is where you saw significant amounts of Mount Mazama ash. Now they say this actually went all the way around the world, and I could believe it, but if you want to talk about deposition, this is where it happened. But the thing is when we got into these drier zones where there's not a lot of vegetation to hold it, you give it a chance to dry and be re-entrained through wind. We always have these kind of southwest to northeast wind patterns in this region. Here's Crater Lake. It deposited all across this region. But a lot of the volcanic ash that fell into here, we're kind of fortunate being in Idaho. The darker the color, the more there is. The lighter the color, the less it is. We just got slugged with that volcanic ash when it came over and hit us. In fact, it just dumped up here in Idaho. In fact, a lot of our private timber company are like, this is great, because why is that important? It's important because of this. Mineralogy. So not only, here's some mineralogy of a thin section of what it looks like within a volcanic ash. Think of surface area. Think of nutrient retention because of surface area. Think of water holding capacity. Here's a glass particle. If you ever had glasses and you dropped them in volcanic ash and you just absent-mindedly just started kind of cleaning them off, don't ever do that in volcanic ash. I did that last summer. I should have known better. And I was just like, why is there scratches all over my glasses now? Well, it's this glass. About 35% of a soil profile can be made up of glass in your ash cap soils. Now, glass is what? It's silica. I just got done telling you silica's bad, right? Well, no. In this case, silica is actually good. Why is that? Look at the surface area and look at all these little holes all over that. So, in this case, imagine from the water holding capacity. In fact, you don't even have to imagine, you can just look at it here. So this is a glacial till soil sitting down here, in some valley bottom, and here's a deep volcanic ash soil sitting on top of it. The UI Soil Laboratory did a characterization of plant available water between those two different soils. In your ash cap soil, anywhere from 20 to 30 up to 40% water holding capacity in your ash cap, varied with depth because then it starts kind of mixing with your glacial material underneath. But look at the difference with your glacial materials. 10% water holding capacity versus somewhere between 20 and even up to 40. So what does this mean from drought stress? Think of drought stress. In the dry interior northwest, where we don't get a lot of rainfall, if this soil can hold that water longer, it can grow longer into the growing season, or it's a buffer to drought. So can you imagine what our forest types would have looked like if we hadn't had volcanic ash in this region? Yes.
Well, also with a 35% silica content in the soil, it seems to me that that would improve the soil friability or the resistance to compaction.
That is a very important point. Volcanic ash has a very low bulk density. So, when you think about it, in fact, we get tree planters coming into our region. They love planting volcanic ash soils because what? Just because of that issue. There's low cohesiveness, there's little structure, coarse fraction's low, so aeration, water holding capacity, very high. Where the problem comes in is because of that, if you get on that volcanic ash at the wrong time of year, that number one, it's displaced really easily. Goes out. Now, if you get on it when it's too wet, what happens is, because of that glass, it compacts and it locks together. Now, here's the thing. Compacted ash caps rarely get above 1 for a bulk density. Growth limiting bulk densities for plants, typically, like when you think of clays, compacted clays, 1.2, 1.3 for a bulk density where you start having some issues. So we don't know, though, if that compaction is an issue, because from a root perspective, that's not limiting from a root penetration perspective, but you're going to have some issues. You're going to decrease your water holding capacity and those kinds of things. So you really do have to be careful with volcanic ash soils, but you're right. From a planting medium perspective, from a root medium, in fact, if you dig, let's go back here real quick to one of these pictures. I should have pointed this out. I don't know if you can see it in that picture, but where do all the roots stop? Yeah. I mean, look at that. They hit that soil parent material. Oh, you see some finer roots going down, right? But where's the bulk of those roots? They're sitting right in that volcanic ash. Because it's just like, why do I need to go anywhere else? Because this is where the water is. So that's very critical. So forest habitats. When we get into our very different forest habitats, we can have shifts in plant communities rapidly based just on volcanic ash. So there's one theory that we probably didn't have a lot of cedar hemlock types in this particular region given the similar climate regimes until we had the volcanic ash on our forest soils just because of that water holding capacity. So essentially the theory is we have essentially shifted, a lot of our sites shifted up a vegetation series based just on the aspect of this volcanic ash. So just to summarize real quick, volcanic ash soils, it's all about water, water, water. Very little about nutrition. There's some iron, there's some potassium, there's some other nutrients in there. There's a lot of silica. But really, it's not really from a nutrition perspective. It's from a drought stress perspective. The other interesting aspect about volcanic ash, and I skipped over that slide because I think we're getting rapidly towards the end here, and I have some things I want to definitely go over, is ash is kind of different than clay soils. Clay soils have the ability to retain cations, calcium, potassium, magnesium. Volcanic ash soils actually can retain anions. And what are anions? Anions is nitrogen, nitrate, NO3 with a minus sign. It's phosphate at PO4, 2 minus. PO3, 2 minus? Can't quite remember. Sulfate, SO4, 2 minus. Those are all anions. Ash caps can hold on to that. So it actually has what we call an anion exchange capacity. So having an ash cap not only increases your water holding capacity, it can actually hold on to, and what did we say were two of the most critical nutrients that are deficient in this region? Nitrogen and sulfur. Ash caps can hold on to it. Okay, let's just tie this all together then, how we can look at this, because now we've been able to bin up our sites. We can look at things from a kind of climatic regime with our parent material or our veg series. We can look at our soils, and then let's look at it from kind of a growth perspective. So we can then look at our different rock types. Mixed is just glacial. We just put mixed as a glacial term in here. We look at our different habitat types. So here's our wet types, cedar hemlock. Here's our moist types, our grand fir, and here's our dry types for duck fir. And this is cubic feet per acre, typical growth on these different rock types. What we'll notice is our glacial types typically are less productive. Metasediments are Similar, maybe a little bit higher on our cedar hemlock types, and our granitics and our basalts tend to be more productive unless you get on the dry sites, your Doug fir series, dry, right? If you don't have water, you're not going to be as productive. So this is a good illustration between your granitics and your basalts that as moisture inputs increase, productivity is going to be best on those particular sites. Why do you think we didn't have any growth numbers in our metasedimentary rock over here on our Doug fir type? Why do you think we didn't have? This was an experiment we put in to look at volume growth, forest health on these different, this was our bins now. This is our veg series for climate and our rock types for nutrients. Why do you think we weren't there?
Doug fir doesn't grow in those soils?
Doug fir was there.
No nitrogen.
Not enough moisture capacity?
All of the above. Those sites were so unhealthy, we couldn't put any research sites into them. Disease, decay. There was nothing healthy enough on those stands that we could actually put in a health study. That's how bad those sites can be when you get into that. So bad rock sites on our dry types. When you get into cedar hemlock, these had a lot of ash caps on them. So a lot of our ash caps on our metaseds actually were very productive. As you went down, these sites had no ash cap. Low productivity, low forest health. So that was very informative. Then we looked at the presence or absence of volcanic ash on growth rate. This is cubic feet per acre per year. And what we saw was kind of mixed. Mixed is mixed. I mean, that's why when we went into our glacials, it was just a mixed bag, literally. It was typically, they were, that range of productivity. But when you went on to our metaseds, remember back to that graphic where we showed we didn't see anything on Doug fir. Well, this is critical. On our metasedimentary sites, if you've got an ash cap, you're going to be more productive. It just goes without saying. Granitics, it had an improvement. Basalts didn't really show any improvement. Why do you think that is?
Well, the ash is really just pulverized granite and basalt.
Good point. So from a water perspective, why do you think the ash over here, and this, I think I see where we're going from a nutrient perspective, but for the most part, volcanic ash it's not really a player when it comes to nutrition. So why would it be over here on our metasedimentaries and our granites have an impact, but it wouldn't on our basalt soils?
The grain size and surface area?
There you go. So it's all about texture. Your basalts are already fine textured, right? So it already has a very high water holding capacity. Our metaseds and our granites, because of the silica content, are usually more coarse textured. You're not going to have as much water holding capacity, so you throw an ash cap on there. Bang. Yeah, water, water, water. So overall, you look at your growth rates, just having an ash cap overall gives you about a 30% increase in growth rate, just having an ash cap. And if you look at this from a nitrogen fertilization perspective, looking at response, so this is cubic feet per acre per year, you can have up to a 50% growth response just by having an ash cap. Now, you got a response on sites with no ash, about 20 cubic feet per acre per year. You can get about 50% more just with an ash cap. And it's because why? You can put as much nitrogen or fertilization out there, but if you don't have water, you're not going to respond to it. So if you have water, you can respond to it. So this is just a 10-year percent response graphic. So at 0.1 is at 10%, 0.8 would be at 80%. We're looking at increasing amounts of nitrogen. All these spaghetti curves just reference different veg series, so Doug fir veg series, gran fir veg series, cedar series, and these are different kind of rock types: basalts, glacials, granitics, mixed as glacials again. Okay, there's some metaseds. But essentially what we can see is there's not a linear response to our nutrient additions, particularly for nitrogen. In fact, in some cases, we actually dropped when we put on higher rates of nitrogen. So 200 to 300 seemed across all sites to be typical. Why did it drop down? Why, by putting more nitrogen out there, did we actually decrease productivity relative to a lower rate? What do you think happened?
The ratio of nitrogen to other nutrients?
Part of it. Sometimes we didn't have enough sulfur on the site to take advantage of the nitrogen or that amount. But the other more critical thing is we actually could increase mortality by putting N only out there. Why could you increase mortality by giving it higher rates of nitrogen?
Does it increase water demand of the plant?
If you are giving a site, if you're overgrowing the capacity of that site, you're going to do what? You're going to stress your tree. If you stress your tree, what's going to happen? Bugs and root rots. So you put this much nitrogen out there, you're going to create an imbalance in your nutrients. You're going to create higher sugar to phenol ratios. Phenols are defensive characteristics. Sugars are your growth, right? So if you have more sugars than phenols, what do root rots and bugs love? Oh yeah, it's sugar. I mean, it's just like you gave them chocolate candy bars to eat. They're going to go crazy, and so they're going to go after those trees. So if they're not stressed, they're imbalanced. Same result. So points to consider when you're going through this whole process of, if I have, do I need to fertilize because why? Do I have nutrient deficiencies or do I want to increase growth rate? If it's from a forest health perspective, typically you might want to look at lower rates of nitrogen in concert with some of the other nutrients. If it's for productivity, do you want to do an N-only application? On some sites, you don't want to do an N-only application because you're creating Liebig's barrel. Anybody familiar with Liebig's barrel, that kind of the most limiting nutrient on the site? Well, if you take care of it, but you don't take care of the stave next to it, which could be sulfur or boron, that could create an imbalance on that particular tree or particular site, and you could create a problem. So you have to be aware of site conditions so you properly diagnose what nutrients you have to put on from a forest health perspective or from a forest productivity perspective. And you could do that by looking at critical nutrient levels in your foliage. What is the moisture regime? I keep hammering moisture regime. It's critical. Trees need water, just like we do. If you don't have water, you could put fertilizer out there and it'll just sit there. In fact, we did a bunch of fertilization studies in some pine stands up by Lubricht, just east of town here. We got zero response. None. Why? We should have realized it. It was before we kind of figured out this whole issue with moisture regime. It's just because something needs something, if it doesn't have water, it's not going to respond. So we came up with this kind of rule of thumb, 25 to 30 inches of annual precip if you want to start to see a growth response to a nitrogen fertilization. Age and composition of your stand. If you have a stand that's old, so just think of a stand with tops are kind of rounded, flat topped, versus something that's like a spire. If you've got a flat top stand and it's older, it's not going to respond. It's shut down. It's stopped. It's not. You could put fertilizer out there all day long and you're never going to see a response. So your old stands and your shade intolerant stands. So think pine. Pines, particularly ponderosa pine. You can typically fertilize ponderosa pine. You hardly even see it budge when you put nitrogen out there. And the reason for that is it's very conservative with its nutrients. It will shut down growth because it is designed to grow in harsh conditions. And so because of that, you could try to tweak the environment, but it's fine with its environment. When you get into your more climax species, grand fir, cedars, hemlocks, Douglas fir is not climax, but more your shade species that are more capable of being shade tolerant, higher productivity rates, then you're going to start seeing responses. This is the most critical point too, is do you have root rot or infestation? If you have root rot and infestation, never, even though if it's nitrogen deficient, never fertilize with just nitrogen because it's so deficient in everything else, you're going to create imbalances. There's going to be deficiencies. So watch out for that. You got to fertilize, if you're going to fertilize, look at it from a perspective of a multi-nutrient approach. Baseline growth. You could increase growth on something that's slow, but a lot of nothing is still nothing.
Right.
And so if it's growing slowly and you double its rate of growth, it's still not going to be much, right? It's still not. Because why? You have to carry those costs. It's all about carrying costs. If you're going to carry this longer term, if you have a low growth rate, you're not going to see a return on your investment. You're just not. So typically, the longer you carry those costs, the greater the response has to be. If you're doing it from a productivity perspective and you want to increase growth rates, you have to carry those costs a lot longer. If you have to have a longer longer response and a greater response to those applications of nutrients. So the rule of thumb is typically you want to harvest within 10 to 15 years of fertilization, because that's usually after about 10 years you see no more response to your fertilization. You have that massive amount of growth typically that you got over that 10-year period, but then it goes back to site growth rates. And so you're not going to gain anything more from having fertilizer on that site, so you might as well capture that effect from your growth. Typical rule of thumb is about 20% growth response to get a meaningful ROI. Now, why we say that is a lot of this there's a lot of costs. Cost of fertilization, cost of application, carrying costs, all that adds up. So typically a 20% growth response rate might get you a 3 to 4% return on investment. So in today's climate, that's awesome, right? You couldn't put your money in the bank and get 3 to 4%. So that's decent. On a lot of the other like private timber companies and things, they look at this more around the 30% range. So to summarize this, we have region-wide nitrogen limitations. Our growth response can be up to 40%, but you have to look at the site moisture regime and the nutrition based on that geology of that site. If you have sites that are poor forest health, you want to consider other kinds of things. You want to look at that more from a forest health perspective than a forest productivity perspective. Healthy forest is a productive forest, but on certain kinds of stands, you're not in there to produce biomass. You're there to make them resilient to insects and disease. And so in cases like that, you might be fertilizing more with potassium, sulfur, boron. You might not even look at nitrogen, or just enough nitrogen to maintain balance. And of course, water, water, water. So it's lunchtime, right? So I'm just going to go over this. I'm going to go right to the end here on this particular case. This kind of summarizes what kind of management activities one might do that has impact on nutrient capital. So we have some baseline. We can look at rotation lengths, intensity utilization, or replacement rate. Essentially what this is saying is on a particular site, if you have an adequate length of rotation, that site will recover to what it was before harvest. In other words, because remember, you're taking trees off, you're taking nutrients off. Appropriate length of time, it'll get back to where it was. If you go to shorter rotations, there is the potential that you'll actually reduce the amount of nutrition on that particular site, degrading it. Intensity utilization, stem only, bowl only harvesting versus whole tree. If you have a certain stock level or a nutrition level on that particular site, if that is a very poor nutrition site and you do whole tree harvesting and taking all those nutrients off, you have the potential of degrading that site versus if you leave the tops and limbs on. Because where is the bulk of all those nutrients? It's in that foliage. It's in the fine materials. And if you can leave those on there, you keep the site nutrient capital. If you have a rapid replacement rate of your nutrients versus slow. If you harvest on a site with a rapid replacement rate, it'll bounce back and you won't have a negative impact as opposed to, so let's just say basalt versus a quartz site, right? So you can actually kind of turn this into a dichotomous key of, okay, what should I do on this site? If we have a site that has a lot of moisture, it has a rapid mineralization replacement rate, and we do bull-only harvesting, we probably will never have an effect on the site nutrient capital and never degrade that site. If we do a short rotation with whole tree harvesting on something with a slow mineralization replacement rate, what's going to happen? You're going to have a grassland. You know, you're going to take the trees off and nothing's going to grow. And we learned this the hard way on Striped Peak and the Rivali Metaseds, particularly Striped Peak over North Idaho. We went and we harvested a lot of these poor nutrient sites, whole tree harvested, windrowed it. So that's, I mean, we're going in with D8s, putting traditional kind of southern silviculture. You pile everything into windrows, you light it. They planted it back. Ponderosa pine hardly even comes back on these sites. They used to be kind of decadent grand fir, Doug fir type stands. They can't even hardly get pine to grow on it. It's because we altered the whole site characteristics on that site. So Yes.
Can you describe the whole tree harvesting versus,
Bowl only.
yeah?
So whole tree would be where you cut the tree at the base and you have a tractor or skidder come in and pull the whole thing to a landing. They process it. All the limbs and the tops go into a pile at the road and then it's burned. Whereas bowl only is they'll go out there with a harvester of some kind and process the tree in the field, which leaves the tops and the limbs out there, and then they just haul the bowl back to the landing. Yeah.
And what about burning slash as opposed to just scattering it?
Well, the fire. We always have this discussion with the fire managers and the foresters, because many of us we're under restrictions, right, on how much slash can be left on a site, just from a fire hazard perspective. And so we always tell the foresters, get as much of that slash left on site as the fire folks will let you, because the more you can leave on site, you can never hurt having more slash on site, right? And so every site's different, of course. You could actually, on a basalt site, you may not really have to worry too much about whole tree harvesting, just because if it's on a warm, moist site and you have basalt soil, that replacement rate is so high on that site and the organic inputs are so high because it's a productive site, you probably never even have to worry about it. But if you get on a quartz site or some sort of low productive soil from a nutrition perspective, then we just recommend just maximize how much they'll allow you to leave out there. Yeah. So 4 minutes over. But hopefully they haven't ate all dinner yet. Any other questions? Not. Thank you. I appreciate the opportunity.
Thank you. Thank you for bringing in.